Right now, physicists cannot explain why you cannot go back to yesterday. Every law of nature is perfectly reversible. A particle collision looks identical forward or backward, and yet a broken glass never reassembles. Time moves in one direction only, and nothing in the equations says why. In the tunnels beneath Geneva, scientists caught this asymmetry in the act. For the first time in history, what they found confirmed the arrow of time. But it opened a darker question. Why did the universe begin with enough order for time to have direction at all? We will follow that question to the edge of everything. If you enjoy this journey, a like and subscribe means the world. Take a breath. We begin. There is a question in physics so deceptively simple that most people never think to ask it. You do not need a telescope to observe it. You do not need a laboratory. You can feel it right now, in the slow cooling of your body against the sheets, in the quiet settling of the building around you, in the way this night moves only forward and never back. The question is this: why does time only move in one direction? You already feel the answer is obvious. Of course, time moves forward. It always has. The past is fixed and unreachable. The future is open and unknown. Between them flows this irreversible current called the present, carrying everything with it. But physicists are professionally dissatisfied with obvious answers. When they looked carefully at the fundamental equations governing how the universe works, they discovered something that should not be possible. Something that contradicts almost everything our senses tell us. The laws of physics, at their deepest level, do not distinguish between the past and the future. At the scale of particles, at the scale of forces, at the level where the universe actually operates, time is perfectly reversible. Nothing in the mathematics forbids a shattered glass from reassembling itself. Nothing in the equations prevents scrambled eggs from spontaneously returning to their original form. The universe has no built-in arrow, and yet here we are, moving in one direction only, watching everything slowly break down, watching time pass in a way it seems it can never undo. This puzzle has a name. Physicists call it the arrow of time, and it may be the deepest unsolved problem in all of science. The strange part is not just that time moves forward. The strange part is that the laws of nature, written carefully and tested against every experiment ever performed, seem to allow time to move in either direction. A recording of two hydrogen atoms colliding and bouncing apart looks identical whether you play it forward or backward. There is no way to tell which is real. But zoom out to a cup of coffee cooling on a table, and you can tell immediately. Play that backward, and the coffee spontaneously heats itself from the ambient air, and the cooling stops. That never happens. Not once. Not anywhere. Not ever. So where does the arrow come from? Why do the microscopic laws allow both directions, while the macroscopic universe insists on only one? The answer involves a concept so fundamental it shapes every process in the cosmos, from the burning of stars to the firing of neurons. It is called entropy, and understanding it will take you somewhere you may not have expected. To a quiet experiment running deep beneath the mountains of Switzerland, where scientists were trying to catch time itself in the act of being asymmetric. The answer they found confirmed something extraordinary, and it opened a question even deeper than the one they were trying to close. What you are about to hear is not speculation. It is some of the most rigorously tested science ever produced, and it will change the way you think about every moment you have ever lived. But what comes next reaches even further back than any experiment. It reaches all the way to the first instant of everything. Picture a short film. 2 billiard balls roll toward each other across a green felt surface, collide with a sharp crack, and bounce cleanly apart. Now, picture that same film played in reverse. The balls roll toward each other, collide, and bounce apart. You cannot tell the difference. The physics looks identical in both directions, because, at that scale, it is identical. This is not a coincidence of billiard balls. It is a deep feature of how nature operates at the particle level. Every fundamental interaction, every collision, every force, every exchange of energy between elementary particles obeys equations that are symmetric with respect to time. Run the film forward or backward, and the equations are satisfied either way. Physicists call this time reversal symmetry, and it holds with extraordinary precision across particle physics experiments performed over decades. Now, picture a different film. A glass sits on the edge of a wooden table. It falls. It strikes the floor and shatters into dozens of fragments, sending shards skidding across the tiles. You would not need to think for even half a second about which direction this film is playing. The shattering moves only one way. The pieces never leap up from the floor, spiral inward through the air, and reassemble themselves back onto the table as a perfect, unbroken glass. The laws of physics do not absolutely forbid this. The atoms in those shards are obeying the same equations as always, but something makes the reassembly so extraordinarily unlikely that it has never been observed anywhere in the known universe, not once in the billions of years since time began. That something is entropy, and entropy is one of the most important ideas in all of science, even though it operates not at the level of individual particles, but at the level of systems, collections, and the universe considered as a whole. Here is the simplest way to understand it. A glass sitting intact on a table represents one specific arrangement of atoms. A shattered glass represents an enormous number of possible arrangements, each slightly different from the last, depending on exactly how the pieces landed. When you drop the glass, it moves from that one precise intact arrangement into one of countless broken arrangements, simply because there are so many more disordered possibilities than ordered ones. Think of it this way. If you took all the fragments and shook them inside a box for 1,000 years, the odds of them spontaneously assembling back into a perfect glass are so close to zero that the difference is meaningless. Any random rearrangement is overwhelmingly likely to produce something broken. This is why things tend toward disorder over time, not because disorder is somehow attracted to the universe, but because disorder vastly outnumbers order in the space of possible arrangements. The mathematics of probability does the rest. The second law of thermodynamics formalizes this observation. It states that, in any closed system, entropy, meaning the measure of disorder, always increases or stays the same. It never decreases. This law has never been observed to fail at a scale we can see with our eyes or our instruments. And here is the connection to time. The past is always the direction of lower entropy. The future is always the direction of higher entropy. The arrow of time, the reason tonight cannot replay itself backward, is the arrow of increasing disorder. But buried inside this elegant explanation is a problem that almost nobody noticed for nearly a century. And when they finally saw it, it pointed all the way back to the beginning of everything. The word entropy gets used loosely in everyday conversation, dropped into sentences as a synonym for chaos or decay. But the scientific meaning is more precise, more beautiful, and in some ways more unsettling than the casual version suggests. In the formal language of physics, entropy measures the number of microscopic arrangements that a system could be in while still appearing the same from the outside. The arrangement you can see matters less than all the possible hidden arrangements beneath the surface. A freshly shuffled deck of cards in a specific order has low entropy, because there are very few ways to arrange those cards and still get exactly that sequence. A randomly shuffled deck has high entropy, because there are an astronomical number of ways to produce a shuffled-looking result. This was first understood deeply by an Austrian physicist named Ludwig Boltzmann, who worked in the latter half of the 1800s. Boltzmann had a vision of enormous ambition. He wanted to explain heat, temperature, and the flow of energy entirely in terms of the movements of individual atoms and molecules. At a time when the existence of atoms was still debated, this was a radical proposal. His insight was that temperature is simply the average kinetic energy of particles moving randomly in a substance. Heat flows from hot objects to cold ones because particles in the hotter region are moving faster on average, and when they collide with slower particles nearby, they transfer some of that motion. The entropy of a system, in Boltzmann's view, is a precise measure of the number of microscopic states consistent with what you observe at the macroscopic level. The higher the entropy, the more ways the microscopic world could be arranged to produce the same visible result. And because higher entropy states are more numerous, systems naturally tend toward them over time, not because of any mystical force, simply because there are more of them, and any random change is statistically likely to land in one. Now here is where this becomes deeply connected to your experience of time. Your cold coffee sitting on the table has higher entropy than it had when it was freshly poured and steaming. The heat has spread into the surrounding air, increasing the disorder of the air molecules, while decreasing the orderliness of the temperature distribution. Returning the coffee to its hot state would require gathering that dispersed heat back together, reducing entropy. That would require fighting the overwhelming probability of dispersal. The same logic applies to everything. Your memories represent physical structures in your brain, arrangements of neurons that were formed when entropy increased during the events being remembered. The sunlight entering your window has been on a journey from a region of extreme order to the diffuse warmth spreading across your floor. Every candle flame, every breath, every heartbeat moves entropy upward and time forward. Boltzmann understood all of this with extraordinary clarity. He also understood the implication that many of his contemporaries found disturbing. If entropy always increases, and if the universe has been increasing in entropy since the beginning, then the beginning must have been in an extraordinarily low entropy state, an improbably ordered state, a state that the statistics of probability suggest should be essentially impossible. Why did the universe start that way? Boltzmann spent years wrestling with this question. He did not live to see it answered, and in a meaningful sense, it has still not been answered today. But the clues, when they came, arrived from the most unexpected direction. Follow the logic of entropy backward through time, all the way to the very beginning, and you arrive at a conclusion that is both inescapable and deeply strange. If entropy always increases as time moves forward, then the further back in time you go, the lower the entropy must have been. The very first moment of the universe must have been in a state of almost incomprehensible order. This is not poetic language, it is a mathematical necessity. The thermodynamic arrow points in the direction of increasing disorder. That arrow had to start somewhere, and wherever it started, entropy had to be lower than it is now, which means lower than it was 1 billion years ago, which means lower than it was 1 billion years before that. Trace the line backward far enough and you reach a beginning that was extraordinarily, perhaps impossibly, organized. Here is why this is so troubling. Imagine listing every possible way the universe could have begun, every possible distribution of matter and energy, every possible arrangement of particles across all of space, every possible starting configuration that physics would allow. Among all of those possibilities, the overwhelming majority are high entropy starting points. Universes that began already disordered, already uniform in their randomness, with no gradient, no structure, no capacity for interesting things to happen. The universe we actually inhabit began in one of the vanishingly rare low-entropy configurations. The physicist Roger Penrose devoted significant effort to quantifying just how rare, and arrived at a probability so small that expressing it requires a number with more zeros than there are particles in the observable universe. Our actual beginning was not just unlikely, it was extraordinarily, almost grotesquely unlikely. And yet, it happened. And because it happened, stars can burn, which means planets can form, which means chemistry can work, which means you can be lying here right now, drawing breath in the quiet dark. Some physicists find this acceptable as a starting point. They invoke what is called the anthropic argument. We observe a universe with a low entropy beginning because only such universes produce observers capable of asking the question. If the universe had begun in a high entropy state, there would be nothing organized enough to notice. Our existence selects for the improbable initial condition, and no deeper explanation is required. Others find this answer deeply unsatisfying. They feel that physics should not rely on our own existence as an explanation for the structure of the cosmos. They want a mechanism, a reason, a deeper principle that makes the low entropy beginning an expected outcome. This disagreement is not resolved. It sits at the center of modern cosmology, like a question mark carved into the foundations of the discipline. What everyone agrees on is this: the arrow of time, the fundamental reason that tonight moves forward and never back, that memories only form in one direction, that stars burn rather than assemble, is a consequence of the low entropy beginning of the universe. Every moment of directed time, every irreversible process, every broken glass and cold coffee and aging face traces its cause back to that one extraordinary starting point. Why that starting point existed is a question physics is still reaching for, but physicists have not been content to simply wonder. They built machines to look for answers, and the machine they built beneath the mountains of Switzerland found something no one had ever observed before. Something is coming that changes everything about how the story continues. The European Organization for Nuclear Research occupies a stretch of land straddling the border between Switzerland and France, in a flat valley that opens toward the Jura Mountains to the northwest and the Alps to the southeast. The surface facilities look ordinary enough, a collection of administrative buildings, laboratories, and computing centers spread across several square miles of European countryside. Bicycles lean against walls. Scientists drink coffee in outdoor cafes. The Rhone Valley hums in the background. But most of the important work happens underground, in tunnels and caverns bored through the rock and clay beneath the foothills. Some of those tunnels are enormous, large enough to drive a vehicle through, stretching for miles in great circular loops. Others are smaller, service passages connecting the major experimental halls where the actual physics takes place. The organization was founded in 1954, a deliberate act of reconstruction in the aftermath of the Second World War. 12 European nations decided that science could serve as a bridge across the political fractures the war had created. They pooled resources to build a facility no single country could afford, dedicated to questions too large and expensive for any national program to answer alone. Over the following decades, the facility became the most important particle physics laboratory on the planet. Its accelerators pushed particles to velocities approaching that of light, smashing them together with energies that recreated, briefly, conditions similar to those in the first fractions of a second after the Big Bang. The results filled in the map of the subatomic world, identifying quarks and gluons and force-carrying particles, assembling what physicists now call the Standard Model. In the 1990s, among the many experiments running simultaneously across the complex, there was a relatively modest one called CPLEAR. It occupied a section of one of the older accelerator rings. It was not searching for a new particle. It was not trying to detect a new force. It had a quieter, stranger ambition. CPLEAR wanted to watch time behave differently in two directions. The experiment was designed to test what physicists call time reversal symmetry. The question was whether the laws of physics at the particle level look exactly the same, whether time runs forward or backward. For decades, most physicists had assumed the answer was yes, with minor, well-understood exceptions. The fundamental equations seemed symmetric. The Standard Model seemed symmetric. The universe at its deepest level seemed indifferent to which way the clock was running. CPLEAR was built to test this assumption with more precision than had ever been attempted, to directly compare the behavior of a particle system moving forward in time with the behavior of the time-reversed process. If the rates were different, if the particle behaved differently depending on direction, it would be the first direct evidence of a microscopic arrow of time. The detector was assembled carefully, calibrated repeatedly, and surrounded with shielding to reduce background noise. The team was patient. Particle physics requires patience. You build the instrument, you collect the data, you check and recheck for sources of error, and then you do it again to make sure. By the time the results were ready, the CPLEAR team had been working for years. What they found was small in magnitude, but enormous in significance, and the implications reached far beyond the tunnels beneath Geneva, all the way back to the first moments of time itself. But first, you need to understand what they were actually measuring, and for that, you need to meet one of the strangest particles in nature. There is a particle called a kaon, and it is unlike almost anything else in the subatomic world. You will never encounter one in ordinary life. They exist only in the violent aftermath of high-energy collisions, lasting for fractions of a second before dissolving into other particles. But in that brief existence, they do something that makes them one of the most fascinating objects in all of physics. A neutral kaon can spontaneously transform into its own antiparticle, the antikaon, and then transform back again. It flickers between two identities, oscillating between particle and antiparticle in a quantum mechanical rhythm. This behavior, this constant shifting between two states, makes kaons extraordinarily sensitive to the deepest symmetries of nature. Any slight difference in how the laws of physics treat matter versus antimatter will show up, amplified, in the way kaons oscillate. To understand why this matters, it helps to know a little about what kaons are made of. All particles built from quarks carry some combination of the fundamental quark types. The kaon contains a strange quark, which is why physicists originally called it strange in the 1950s, when it turned up unexpectedly in cosmic ray experiments and seemed to behave in ways their theories could not explain. The neutral kaon is a bound combination of a down quark and an anti-strange quark. Its antiparticle carries the reversed combination. Because the particle and antiparticle have different quark content, they interact slightly differently with other particles when they decay. This means that if you can track which type of kaon is present at the beginning and which type of particle it eventually decays into, you can measure the rate of transformation in each direction. Forward in time, how often does an anti-kaon become a kaon? Backward in time, or equivalently, in reverse, how often does a kaon become an anti-kaon? If the laws of physics are perfectly symmetric with respect to time reversal, these two rates should be identical. The transformation should look the same whether you play it forward or backward. If the rates are different, even slightly, it means that nature distinguishes between the two directions. It means there is a microscopic arrow of time built into the behavior of matter at the fundamental level. The detection method is elegant in concept, though demanding in practice. When a kaon or antikaon decays, one of the possible outcomes is the production of a charged lepton, either an electron or a positron. The sign of the charge tells you what type of kaon decayed. Count enough events, compare the rates with enough precision, and you can measure the asymmetry. This was exactly what CPLEAR was designed to do. Antiprotons from the accelerator were aimed at a hydrogen gas target inside the detector. The collisions produced kaons and antikaons in roughly equal numbers, and the detector tracked their subsequent decays through a series of wire chambers, scintillators, and calorimeters arranged in concentric layers around the interaction point. The experiment had to be extraordinarily careful. Any systematic effect that treated kaons and antikaons differently for reasons other than fundamental physics could mimic a real asymmetry. The team spent years checking every possible source of experimental bias. They analyzed the same data multiple ways, looking for any sign that the result might be an artifact rather than a real effect. By the time they finished, they were confident. The asymmetry was real. Time was behaving differently in the two directions. And what they had found reached much further than anyone expected. The CPLEAR collaboration published their final result in 1998, after years of data collection, analysis, and verification. The announcement was made at CERN and simultaneously submitted to the journal Physics Letters. The press release that accompanied it used language unusual for a physics publication. For the first time in the history of physics, a microscopic arrow of time had been directly observed. The measurement itself was remarkably precise, given how small the effect is. The asymmetry between the two transformation rates, anti-kaon becoming kaon versus kaon becoming anti-kaon, was approximately 6 parts in 1,000. That is a tiny number. For every 1,000 kaon transformations you observe, only about 6 of them reveal the directional preference. The overwhelming majority of events look the same in both directions. But 6 out of 1,000, measured with the statistical precision that millions of recorded decays can provide, is unambiguous. What does this number actually mean? In the language of symmetry, it means that time reversal symmetry, the mathematical statement that the laws of physics look the same with time, running forward or backward, is violated by the weak nuclear force. The weak force is responsible for certain types of particle decay, including the oscillation and decay of kaons. And at the level of the weak force, the universe does not treat the past and future identically. This was not entirely unexpected. Years before the CPLEAR measurement, experiments had already established that kaons violated a related symmetry called charge parity symmetry. The combined theorem of charge, parity, and time symmetry, which physicists treat as an essentially inviolable principle of quantum field theory, predicts that if charge parity symmetry is violated, time reversal symmetry must also be violated by exactly the compensating amount. CPLEAR confirmed this prediction directly, for the first time, without relying on the indirect argument. The measurement was subsequently confirmed by an independent experiment at the Fermi National Accelerator Laboratory in the United States, using a completely different technique and detector design. The result held. Time reversal violation in kaons is a real, reproducible, experimentally solid fact. In the years following the initial measurement, similar asymmetries were discovered in other particle systems, particularly in particles called B mesons, which contain bottom quarks and show charge parity violation at a much larger level than kaons. Experiments at particle colliders around the world have mapped these asymmetries in increasing detail, confirming and extending the picture that kaons first revealed. At this point, you might be wondering what a 6 in 1,000 asymmetry in an exotic particle has to do with the large-scale arrow of time you experience every moment of your life. The honest answer is less than the headlines suggested at the time. The microscopic time asymmetry found by CPLEAR and the thermodynamic arrow of time that governs your experience are related in spirit, but not the same phenomenon. The thermodynamic arrow is driven by entropy and the initial conditions of the universe. The particle asymmetry is driven by the specific behavior of the weak force. But the particle asymmetry points towards something even more significant than the arrow of time. It points toward the reason the universe contains anything at all. It is a thread that, when you follow it, leads to the first second of creation. And what happened in that first second is the story behind every atom in your body. According to the best physics we have, the Big Bang should have created equal amounts of matter and antimatter. Every proton produced in those first fractions of a second should have been accompanied by an antiproton, every electron by a positron, every quark by an antiquark. The creation of particles from pure energy which is what happened as the universe cooled from its initial extreme density, should have been perfectly symmetric between matter and its mirror. When matter and antimatter meet, they annihilate. They convert entirely back into energy, leaving nothing behind except light. If the universe had been created with a perfectly equal mixture, every particle would eventually have found its antiparticle, and everything would have annihilated. The cosmos would be nothing but a thin, expanding bath of light, with no atoms, no molecules, no stars, no planets, no observers of any kind. And yet, here you are. The universe contains matter. Vast, overwhelming, extraordinary quantities of matter. Galaxies stretching for hundreds of thousands of light years, containing hundreds of billions of stars, each star containing more atoms than there are grains of sand on every beach of every continent on the Earth. All of that is made of matter, with essentially no antimatter to be found anywhere in the observable universe. Something in the first moments broke the symmetry. Slightly more matter was created than antimatter. The excess was tiny by proportional standards, roughly 1 part in a billion. But that tiny residue, left standing after the great annihilation, is the entirety of the physical world as we know it. Every galaxy, every star, every planet, every person, every atom in the known universe is the leftover excess from that asymmetry. For this imbalance to occur, certain conditions must be met, conditions that were first identified by the Soviet physicist Andrei Sakharov in 1967. One of those conditions is the violation of charge parity symmetry, the same symmetry whose violation is connected to the time reversal asymmetry measured at CERN. The Kaons experiments and the B. Meson experiments that followed confirmed that charge parity symmetry is indeed violated in nature. However, there is a significant problem. The amount of charge parity violation observed in Kaons and B. Mesons, while real, is far too small to account for the observed matter excess in the universe. If the only sources of symmetry violation were the ones we have measured so far, the universe should still be essentially empty. The excess of matter over antimatter should be negligible, orders of magnitude smaller than what we actually observe. This means there are additional sources of charge parity violation that have not yet been discovered. Physics beyond what the standard model predicts. New particles, new interactions, new symmetry-breaking mechanisms operating at energy scales that current accelerators cannot yet reach. The experiments at CERN are part of an ongoing search for these undiscovered mechanisms. What the CPLEAR measurement established, in its careful accounting of 6 parts in 1,000, was that nature is capable of treating matter and antimatter differently. The universe has a preference. That preference, amplified by whatever mechanisms remain to be discovered, turned an otherwise empty cosmos into one containing everything. But there is still the question of where time itself fits into all of this. That question leads back to a beginning so strange it is almost impossible to picture. The Big Bang was not an explosion the way we typically imagine explosions. There was no pre-existing space for it to detonate inside. There was no surrounding void to expand through. No before from which an observer could have watched it begin. The Big Bang was the beginning of space itself, the beginning of time itself, the singular starting point from which all subsequent history unfolds. What physics can tell us about the earliest moments comes from 2 directions simultaneously, from the very large, through astronomical observations of how the universe is structured now, and how that structure has evolved over time, and from the very small, through particle physics experiments that recreate, in miniature, conditions similar to those in the first fractions of a second after the beginning. In those earliest instants, the universe was unimaginably hot and dense. The temperature was so extreme that the concepts we normally use for heat and density become almost meaningless. The 4 fundamental forces of nature, meaning gravity, electromagnetism, and the 2 nuclear forces, may have been unified into a single interaction. As the universe expanded and cooled, these forces separated one by one, each separation releasing energy and changing the character of the cosmos. Quarks condensed from the initial plasma into protons and neutrons. Protons and neutrons combined into the nuclei of hydrogen, helium, and lithium. After hundreds of thousands of years, electrons joined those nuclei to form the first atoms, and the universe became transparent to light for the first time. The light released at that moment is still traveling through the cosmos today, cooled by expansion into a faint microwave glow that fills the entire sky. It is called the cosmic microwave background, and it is the oldest light we can observe. But here is what is most striking about that ancient light. When astronomers measure it with extraordinary precision, they find that it is almost perfectly uniform in every direction. The temperature of the microwave background is the same to roughly 1 part in 100,000, regardless of which direction you point your detector. The early universe was extraordinarily smooth. In thermodynamic terms, this smoothness represents a state of extremely low entropy. The early universe was highly specific in its configuration. The early universe was arranged in a very particular, very constrained configuration, far more particular than the vast majority of possible starting points would have been. And this constraint, this specificity, this extraordinary low entropy beginning, is the origin of the arrow of time. The universe has been running down from that precise starting configuration ever since. Stars formed from the gradual clumping of matter, converting gravitational order into heat and light. Planets accumulated around those stars. Chemistry organized molecules into structures of increasing complexity. And through a chain of processes, each depending on the one before, consciousness arose to wonder about how it all began. Every arrow of time in nature, every asymmetry between past and future, traces its lineage back to those first moments of extraordinary smoothness. The question of why the universe began that way remains one of the deepest open problems in physics. But it is not just an abstract puzzle. It is the reason you exist to ask it, and what comes next makes the puzzle considerably stranger. Picture the space of all possible universes, all the different ways the Big Bang could have begun, all the possible distributions of matter and energy, all the configurations that physics would permit as starting conditions. This space is unimaginably vast. The number of possible initial states for the observable universe alone is a number that cannot be expressed in any notation a human mind can meaningfully grasp. Among all of those possible starting points, the overwhelming majority would produce universes already in high entropy states from the first moment. Universes that began maximally disordered, with no gradients, no temperature differences, no structure for gravity to organize, no usable energy for anything to happen. These universes would not expand into complexity. They would simply spread their disorder evenly across space for an eternity, producing nothing. Our universe began in one of the exceptions, one of the vanishingly rare, low-entropy configurations. The physicist Roger Penrose attempted to quantify just how exceptional this is, and arrived at a number so large it defies ordinary imagination. The probability of our particular initial conditions arising by chance is something like 1 divided by 10 raised to a power of 10, raised to the power of 123. To call this a small number is a profound understatement. It is a probability so remote that writing it down requires more digits than there are particles in the observable universe. And yet it happened. There are several schools of thought about what to make of this. The first, already mentioned, is the anthropic argument. We find ourselves in a low-entropy universe because only low-entropy universes produce the kind of complexity necessary for observers to exist. If the initial entropy had been high, there would be no stars, no chemistry, no life, no one to notice the emptiness. Our presence here selects for the improbable starting conditions. The second school of thought holds that the anthropic argument, while logically valid, is scientifically unsatisfying. It explains our observation without explaining the physics. It says why we would see a low entropy beginning, but not why the low entropy beginning exists. These physicists want a mechanism, a deeper principle of nature that makes such beginnings probable or even inevitable. The third school of thought, associated with cosmologists like Sean Carroll, argues that the puzzle can only be resolved by extending our picture of the universe beyond what we can observe. In this view, our cosmos is embedded in a larger structure, perhaps infinite in extent, within which the local low-entropy fluctuation that became our Big Bang was an expected, if rare, event. Each of these perspectives carries consequences that reach far beyond the abstract question of why our universe started so ordered. They have implications for the ultimate fate of the universe, for the nature of time itself, for whether the arrow of time we experience is a fundamental feature of reality or a local accident of our position in a much larger whole. The question is genuinely open, and it connects, in ways that took physicists decades to fully appreciate, to a thought experiment first proposed in the 19th century that seemed, on the surface, to simply be about a box of gas. But hidden inside that thought experiment was a paradox that goes straight to the heart of why you cannot return to yesterday. In 1867, the Scottish physicist James Clerk Maxwell, one of the greatest scientists who ever lived, imagined a scenario designed to test the limits of the second law of thermodynamics. He pictured a small sealed box divided into two equal halves by a thin wall. Both halves were filled with gas at the same temperature, meaning the molecules in each half were moving at roughly the same average speed. In the wall between the two halves, Maxwell imagined a tiny door, controlled by a hypothetical being small enough to observe individual molecules as they approached. This being, which later came to be called Maxwell's demon, watches the molecules flying toward the door. When a fast-moving molecule approaches from the right side, the demon opens the door briefly and allows it to pass into the left side. When a slow-moving molecule approaches from the left, the demon opens the door and lets it through to the right. Over time, the fast molecules accumulate on the left and the slow ones on the right. The left side gets hotter and the right side gets colder. The demon has created a temperature difference from a uniform gas, with no apparent expenditure of energy. The entropy of the gas has decreased. The arrow of time, at least inside this box, appears to have been reversed. This thought experiment troubled physicists for nearly a century. If entropy could be decreased this way, the second law of thermodynamics would not be absolute. The arrow of time would be a statistical tendency rather than a fundamental feature of nature. It seemed to undermine the entire edifice. The resolution came from an unexpected direction. In 1961, the physicist Rolf Landauer showed that the demon must observe and record the molecules in order to sort them. It builds up a memory of which molecule went where, and memory, at a physical level, is a configuration of matter that carries information. When the demon's memory fills up, and it must erase old records to make room for new ones, that erasure generates heat. The entropy created by erasing the memory exactly compensates for the entropy decrease in the gas. The second law holds. The demon cannot win, but the implications of this resolution reach much further than the thought experiment itself. What Landauer showed is that information and entropy are not merely analogous concepts, they are physically the same thing, measured in different units. Information stored in a physical system represents a reduction in entropy. Erasing that information increases entropy. The act of knowing something about a physical system has a thermodynamic cost. This means that the arrow of time is also an arrow of information. The universe moves from a state of organized information toward a state of maximum ignorance. Your memories are thermodynamically expensive structures, formed when entropy-increasing processes left physical traces in your brain. Every thought you have, every perception, every memory of yesterday has an entropic cost. You are a pattern of organized information in a universe that is constantly working to dissolve such patterns. The demon cannot cheat the arrow of time, because the arrow of time is written into the very nature of information. Knowing has a cost, remembering has a cost, and the universe, vast and patient, always collects. But what this means for the deepest levels of physics, for the quantum world where all of this ultimately originates, opens a stranger door still. Drop down to the quantum scale, the level where physics operates in terms of wave functions and probability amplitudes and particles that exist in superpositions of multiple states simultaneously, and the arrow of time becomes subtler and stranger. The central equation of quantum mechanics, the Schrödinger equation, is time reversible. Like all the fundamental equations of physics, it makes no distinction between forward and backward time. A quantum system evolving forward obeys the same mathematics as a quantum system evolving backward. At this level, there is no arrow, and yet when you observe a quantum system, something happens that appears irreversible. Before the measurement, the particle exists in a superposition of possibilities. It has no definite position, no definite energy, no definite state. After the measurement, it has a specific, definite value. The superposition is gone. You cannot undo this. You cannot unmeasure a particle and return it to its quantum blur. This apparent irreversibility in quantum measurement puzzled physicists for decades and still generates philosophical debate. The mainstream explanation involves a process called decoherence. When a quantum system interacts with a larger environment, the possibilities that were quantum mechanically blurred together become entangled with the enormous number of particles in the surrounding world. The quantum coherence spreads out into the environment in a way that is, for all practical purposes, impossible to reverse. Think of it this way. A single coherent quantum state is precisely organized in a specific relationship of phases and amplitudes. When it interacts with a detector, a laboratory, a table, an atmosphere, it becomes entangled with all the atoms of those environments. The information about the original state disperses across an astronomical number of particles. Recovering it would require tracking and reversing every single quantum interaction simultaneously, a task that quickly becomes impossible in every practical sense absolute. Decoherence is a thermodynamic process. The spreading of quantum coherence into the environment is, at the level of quantum information, an increase in entropy. Every quantum measurement, every interaction between a small quantum system and a larger environment is a step in the direction of greater disorder, expressed in the language of quantum information rather than heat and pressure. The quantum arrow of time and the thermodynamic arrow of time are, at this level of description, the same arrow. They are both expressions of the tendency of organized information to disperse into the environment, of coherence to dissolve into entanglement, of order to give way to the overwhelming statistical weight of disorder. What makes this connection beautiful is what it implies about the relationship between knowledge and the physical world. Every act of measurement, every observation, every interaction that we use to learn something about the quantum world leaves a thermodynamic trace. The universe does not permit the acquisition of information without an entropic cost. Knowledge is literally carved into the increasing disorder of the cosmos. And this means the quantum world, strange and counterintuitive as it is, does not escape the arrow of time. It participates in it, contributes to it, and in some interpretations, originates it. But carrying this logic to its ultimate conclusion reveals something about the far future that is genuinely difficult to contemplate. In recent years, headlines have periodically announced that scientists have reversed the arrow of time in the laboratory. These announcements are real, the experiments are genuine and remarkable, and the physics involved is fascinating. But what the experiments actually demonstrate is considerably more subtle than the headlines suggest, and understanding the subtlety reveals something important about what the arrow of time really means. In one class of experiments, physicists prepared pairs of quantum particles in specially correlated states where the two particles share quantum information in a way that creates correlations between their properties. They then allowed heat to flow between these correlated particles. Under ordinary circumstances, heat flows from hot to cold, always. The second law of thermodynamics permits no exceptions at the scale of any system we can directly observe. But in these experiments, something surprising happened. Heat flowed from the cold particle to the hot one. The thermodynamic arrow, locally and briefly, appeared to run backward. Cold, heated, hot. Disorder appeared to decrease. The key to understanding why this does not violate the second law lies in accounting for the full system. The full system, including the quantum correlations between the particles. Those correlations are a form of organized information. They represent low entropy. As the heat flows in the apparent reverse direction, the correlations are consumed. The information encoded in them disperses. The entropy of the correlations increases, even as the entropy of the temperatures decreases. When you count everything, total entropy has still increased. The arrow of time was not reversed. It was redirected, fed by the entropy stored in the quantum correlations, rather than by the entropy difference between temperatures. The second law held completely. In a second category of experiments, physicists used quantum computers to run algorithms backward, effectively time-reversing the evolution of small quantum systems over short timescales. This is genuinely a form of time reversal in a precise mathematical sense. It works because the quantum system involved is extremely simple, containing only a handful of quantum bits, and because the physicist can track and invert every quantum operation with complete precision. Apply the same technique to any real macroscopic system, anything with more than a few dozen particles, and the impossibility becomes apparent immediately. The number of quantum operations required grows exponentially with the number of particles. The quantum correlations between the particles and their environment, accumulated over the history of the system, cannot be tracked or inverted. The practical impossibility is as absolute as any physical law. Time runs forward because the universe is large, because it is deeply entangled with itself across an astronomical number of particles, and because the initial entropy was low enough to create a gradient that all of those particles are collectively running down. No experiment has reversed this gradient. No experiment has found a violation of the second law at any macroscopic scale. What the experiments have shown is the deep connection between quantum information, entropy, and the directionality of time. And that connection has implications that reach much further than the laboratory bench. It reaches all the way to the ultimate destination of the universe, the end state toward which the arrow of time has been pointing since the first moment of creation. That destination has a name, and it is one of the most extraordinary concepts in all of science. Among all the structures in the universe, black holes occupy a unique position in the thermodynamics of time. They are not simply massive objects with strong gravity. They are, in a sense that physicists have only recently come to appreciate, the highest entropy configurations that matter can achieve. Understanding why reveals a profound connection between gravity, information, and the arrow of time. In the 1970s, a young physicist named Jacob Bekenstein proposed something radical. He argued that black holes must have entropy, a definite thermodynamic quantity proportional to the area of their event horizon, the boundary within which nothing, not even light, can escape. Before Bekenstein, the prevailing assumption was that things falling into black holes simply vanished, taking their entropy with them, which would violate the second law. Stephen Hawking initially resisted Bekenstein's idea, then worked through the mathematics and arrived at a result that surprised even himself. Black holes are not entirely black. Quantum effects near the event horizon cause them to emit a faint thermal radiation, now called Hawking radiation. With a temperature inversely proportional to their mass, the radiation carries energy away from the black hole. Over extremely long timescales, a black hole can gradually evaporate. This changed the picture of black hole entropy from a theoretical curiosity to a central problem. If black holes have entropy proportional to their horizon area, and if they can evaporate, then the information about everything that fell in, the detailed microscopic state of all that matter, must somehow be encoded in or transmitted through the radiation. The alternative, that the information is simply destroyed, contradicts quantum mechanics, which holds that information is always conserved, only scrambled and redistributed, never eliminated. This tension between the apparent information loss in black holes and the quantum mechanical requirement that information be preserved is called the black hole information paradox. It has occupied some of the best minds in theoretical physics for 50 years. Its resolution, when it finally arrives, will likely require a synthesis of quantum mechanics and gravity that does not yet exist. But from the perspective of the arrow of time, black holes play another role. As the universe ages and stars exhaust their fuel, matter gradually collapses into black holes. The entropy of the universe continues to increase as organized stellar material becomes the highly disordered thermal radiation emitted by evaporating black holes. Black holes are, in a thermodynamic sense, one of the main ways the universe converts low entropy into high entropy on cosmological timescales. The evaporation of a black hole takes an almost incomprehensibly long time. A black hole with the mass of our nearest star would take longer than 10,000 times the current age of the universe to fully evaporate. A supermassive black hole at the center of a galaxy would take a time whose duration is a number with 80 zeros. But the universe is patient, and the arrow of time points in only one direction. Eventually, every black hole that will ever form will also evaporate, and after that, the universe will enter a phase that has been contemplated theoretically but never directly observed, and perhaps never will be. What comes after the last black hole is a chapter in cosmic history that no conscious being may survive to witness. The arrow of time points toward an end, not the end of any particular civilization, or planet, or star, or galaxy, but the end of the conditions that make any of those things possible. Physicists have traced the logic of increasing entropy forward to its ultimate conclusion, and what they find waiting at the far end of time has a name that captures something true about its character. The heat death of the universe, or thermodynamic equilibrium, is the state toward which every process in the cosmos is slowly, inexorably tending. It is the state of maximum entropy, the configuration in which disorder is as great as it can possibly become, in which every temperature difference has been smoothed out, every energy gradient has been exhausted, every source of usable energy has been spent. The journey from now to then passes through stages almost too vast to contemplate. In the near future, on the scale of billions of years, the ordinary stars will exhaust their fuel. The most massive ones will collapse into neutron stars and black holes. The smaller ones, like the nearest star to Earth, will swell into red giants before cooling slowly into white dwarfs, gradually fading over trillions of years. By the time roughly 100 trillion years have passed, the era of star formation will be over. The remaining stellar material will have been consumed or rejected from galaxies. The universe will be populated by cooling stellar remnants, growing darker and colder decade by decade. Then the slower processes take over. Protons, if current theories are correct, are not stable over infinite timescales. They decay, each decay releasing a tiny burst of energy and leaving behind lighter particles. The timescale for proton decay is estimated at around 10 raised to the 34th years. Long before that, most matter will have been pulled by gravitational interactions into the black holes that populate galaxies, and those black holes will evaporate over their own extraordinary timescales. When the last black hole has radiated away its mass, the universe will consist of a thin, cold, expanding bath of photons and the lightest fundamental particles dispersed through space that is growing larger with every passing moment. Every temperature difference will be gone. Every energy gradient will have dissipated. No process capable of doing work will occur. No complex structures will form or persist. No chemistry will happen. No information will change. The arrow of time will not reverse at this point. Entropy will not decrease, but the arrow will lose its content. There will be nothing left to move from ordered to disordered, because everything will already be at maximum disorder. Time will continue, perhaps, in the sense that one moment will still follow another. But in any meaningful physical sense, nothing will happen. This is the heat death, the final state, the resting point that the universe has been approaching since its improbably ordered beginning. Every fire that has ever burned, every star that has ever shone, every mind that has ever wondered, has been part of the long process of running down from that extraordinary low entropy start toward this maximum entropy end. And yet, even here, the logic of physics does not entirely stop, because in a universe that has reached maximum entropy and exists for a sufficiently long time, the mathematics of statistical mechanics still permits something extraordinary. In a universe that has reached maximum entropy, a universe of maximum disorder and thermal equilibrium stretching in all directions forever, almost nothing ever happens. The particles that remain drift slowly through expanding space, never forming structures, never exchanging significant energy. Time passes in the truest sense of emptiness. But almost nothing is not quite the same as nothing at all. Statistical mechanics, the mathematical framework that describes how large collections of particles behave, never completely forbids any configuration. Even in a system at maximum entropy, random fluctuations occur. Particles drift together and then apart. Tiny temporary reductions in entropy are always possible, though they become exponentially rarer as the size of the fluctuation increases. Most fluctuations would be negligible, a few particles clustering briefly before dispersing. Given enough time, though, and in a universe that has been expanding for long enough, much larger fluctuations become possible. A molecule forming spontaneously, a complex molecule, an organized structure of significant size, even, in principle, a fully functional brain, assembled by pure chance from the thermal bath, complete with sensory experiences and memories of a past that never actually happened. This is the Boltzmann brain, a thought experiment first recognized by Ludwig Boltzmann himself in the late 1900s as a logical consequence of his statistical mechanics applied to an eternal universe. Boltzmann understood that if you wait long enough, any configuration is possible, including a configuration that includes a conscious observer floating in thermal equilibrium, experiencing what seems like a coherent reality. The Boltzmann brain scenario is deeply troubling for a very specific reason. If observers can arise as random fluctuations in a high entropy universe, and if such a universe has been expanding for long enough, then the overwhelming majority of all observers who have ever existed or will ever exist might be Boltzmann brains rather than beings who evolved from a genuine low entropy beginning. The random brain would vastly outnumber the evolved ones simply because the post-heat death era lasts so much longer than the structured era. If most observers are Boltzmann brains, then any given observer, including you, is most likely a Boltzmann brain. Your memories would be illusions. Your sense of living in a lawful universe would be a statistical artifact, and nothing you appear to remember would have actually happened. Most physicists regard the Boltzmann brain conclusion as a reductio ad absurdum, a sign that the reasoning has gone wrong somewhere, rather than as a genuine possibility to take seriously. The fact that you appear to be embedded in a consistent, lawful universe with a genuine history is taken as evidence that you are not a Boltzmann brain. You emerged from the real low entropy beginning, and your memories are genuine records of a real past. But the scenario illustrates how extreme the implications of entropy become when you follow them without flinching, and it reinforces the central mystery. The reason you can trust your memories, the reason the arrow of time has direction, the reason tonight will be followed by tomorrow rather than by a random fluctuation of something indistinguishable from yesterday, is that the universe began improbably ordered. That beginning is doing a great deal of work, and physics has yet to fully explain why it happened. Among the physicists who have thought most carefully and publicly about the arrow of time is a cosmologist named Sean Carroll. His position, developed over many years and explained in books, lectures, and technical papers, is that the low entropy beginning of the universe is a puzzle that demands a physical explanation, and that finding that explanation requires thinking beyond the boundaries of what we can observe. Carroll's argument begins with a challenge to the standard framing. Most discussions of the arrow of time start with the question, given that the early universe had low entropy, why does entropy increase afterward? This question has a straightforward statistical answer, but Carroll argues the real question is different. Why did the early universe have low entropy in the first place? This question has no satisfying answer within standard cosmology, because the Big Bang is treated as a boundary condition, a given starting point, rather than something to be explained. His proposed resolution involves a framework in which our universe is embedded in a much larger structure, sometimes called the multiverse in a specific technical sense. In this picture, the background state of the cosmos is one of extremely high entropy, a featureless near equilibrium that has existed, in some sense, forever. Occasionally, quantum fluctuations in this background produce pockets of lower entropy that expand and evolve according to the same physics as our universe. The Big Bang, in this view, was less the beginning of everything than the moment when one such fluctuation began its expansion. If this picture is correct, the improbably low entropy of our cosmic beginning is no longer mysterious. It is expected, or at least not forbidden, by the properties of the larger structure. We happen to live inside one of the fluctuations, and the fact that our local universe has an arrow of time pointing away from its low entropy birth is simply a consequence of where we find ourselves in the larger whole. The appeal of this proposal is that it dissolves the mystery of the initial conditions without invoking the anthropic argument or requiring a new fundamental principle. The challenge is that it is extraordinarily difficult to test. By definition, the background structure Carroll proposes would exist beyond any horizon we can observe. Any evidence for it would be indirect, perhaps in subtle patterns in the cosmic microwave background, or in the statistics of how structures form in our universe. Other physicists find different solutions more compelling. Some argue that the low entropy beginning follows from a quantum theory of gravity, which would describe the universe as a quantum system with its own wave function, and from which the initial conditions could in principle be derived. Others think that time itself may be fundamentally different at the quantum gravitational level from how we experience it, and that the arrow may emerge from the quantum nature of space-time rather than being imposed as a boundary condition. The question is genuinely unsettled, but following any of these threads leads deeper into the same fundamental mystery: the relationship between time, entropy, information, and the structure of space itself. That relationship has implications that touch physics, as well as the nature of consciousness, memory, and what it means to experience time at all. The connection between entropy, information, and the arrow of time runs much deeper than abstract physics. It runs through the most intimate features of conscious experience. The reason you remember yesterday and cannot remember tomorrow is not merely a fact about your brain. It is a thermodynamic necessity, a consequence of the same principles that govern the cooling of stars and the expansion of galaxies. A memory is a physical structure When an event occurs, it leaves a trace in the world. In your brain, the trace takes the form of modified connections between neurons, changes in the strengths of synapses, alterations in the molecular configuration of neural tissue. These changes are created by processes that increase entropy. The event unfolds, energy flows, disorder increases in the surrounding system, and a low entropy record is left behind in the brain. This is why memories can only form in the forward direction of time. The processes that create them are irreversible thermodynamic events. The broken glass leaves a record in the pattern of shards on the floor. The conversation you had leaves a record in the state of your auditory cortex. The meal you ate leaves records in your bloodstream and your digestive system. All of these records are physical encodings of past events created by the same entropy-increasing processes that define the direction of time. You have no memories of the future for the same reason that broken glasses do not reassemble themselves. It would require thermodynamic processes to run backward, entropy to decrease spontaneously, the overwhelming probability of disorder to give way to the vanishing probability of precise organization. It does not happen. Your sense of being a continuous self, a person who persists from moment to moment and carries a history through time, is itself a thermodynamic construction. It is maintained by a continuous expenditure of energy against the tendency toward disorder. Your body takes in organized chemistry in the form of food and releases heat and metabolic waste. Your brain consumes a disproportionate fraction of your caloric intake to maintain the complex, low entropy patterns of neural organization that support thought, memory, and experience. You are, in the most literal physical sense, a temporary excursion from equilibrium. You exist because there is a thermodynamic gradient between the organized chemistry flowing into you and the dispersed heat flowing out. That gradient ultimately traces back to the nearest star, which burns because the universe began in an ordered state and has been running down ever since. Remove that gradient, cut off the input of organized energy, and the structures that constitute you dissolve back into the thermal equilibrium around them. This is not a metaphor for death. It is an exact thermodynamic description of what death is. It is the cessation of the energy flow that maintains a complex low entropy structure against the overwhelming pull of disorder. All of this might sound bleak, and it carries a certain austere honesty, but there is another way to hold it. You are not simply subject to the arrow of time. You are made of it. Your memories, your experiences, your capacity to wonder about the direction of time, all of it exists because of the extraordinary improbability of the universe's beginning. You are the universe's low entropy, temporarily organized into a form that can ask why. The thermodynamic arrow of time is the most fundamental, the one from which all others derive. But physicists have identified several other arrows, each pointing in the same direction, each connected to entropy in its own way, each offering a different window onto the same underlying asymmetry. The cosmological arrow points in the direction the universe is expanding. The galaxies are moving apart. Space itself is growing. This expansion has been occurring since the Big Bang and, as far as current observations indicate, is accelerating due to a poorly understood energy density that fills otherwise empty space. The cosmological arrow agrees with the thermodynamic arrow. Both point away from the dense, ordered beginning and toward the dispersed, disordered future. Whether the cosmological arrow is independent of the thermodynamic one, or whether it follows from the same initial conditions, is a matter of active discussion. Some physicists think that if the universe were ever to reverse its expansion, the thermodynamic arrow would also reverse. Others, including Stephen Hawking, who spent years revising his own position on this question, argued that the thermodynamic arrow would continue pointing in the same direction even during a cosmic contraction. The radiative arrow describes the behavior of waves, electromagnetic waves, sound waves, water waves, spreading from a point where a stone broke the surface. All of these spread outward from their sources. They do not converge inward. A radio antenna broadcasts in all directions. It does not absorb from all directions. A lamp radiates outward. It does not absorb inward. The time-reversed version of a spreading wave is a converging wave, a spherical shell of electromagnetic radiation collapsing from all directions onto a single point. This is mathematically permitted by Maxwell's equations, which describe how light propagates. Physicists have even created converging waves in laboratory conditions with careful experimental setup, but they require extraordinarily specific and carefully prepared initial conditions, conditions of extremely low entropy. In the natural world, waves spread outward because the disordered, generic, high-entropy initial conditions for a wave are the spreading ones. Just as the disordered initial conditions for a box of gas produce dispersal rather than assembly, the causal arrow says that causes precede effects. You can break an egg today, but the broken egg cannot reach back in time and cause you to have struck it. Causality moves in one direction, and that direction is the thermodynamic one. Past states cause future states, because the processes by which causes produce effects are thermodynamic processes, generating entropy and leaving records as they go. The psychological arrow is perhaps the most intimate. You remember the past and anticipate the future. You have intentions that reach forward in time and memories that reach backward. This, too, is thermodynamic. Memory formation requires entropy-increasing processes. Anticipation is a pattern maintained by continuous energy expenditure against disorder. All of these arrows agree because they are all expressions of the same underlying fact. The universe began improbably ordered, and everything since has been the story of that order slowly, inevitably, and sometimes magnificently dissolving. The arrow of time is not a single phenomenon. It is a family of related asymmetries, all pointing in the same direction, all downstream from one extraordinary beginning. Go outside on a clear night and look up, and you are doing something that no amount of description can fully prepare you for. You are looking back along the arrow of time. Every photon entering your eye has been traveling since before you were born, before your parents were born, before civilization existed, before the nearest star was formed. The night sky is not a view of the present universe. It is a layered record of the past. The light from the nearest star beyond the solar system has been traveling for more than 4 years. What you see when you look at that faint point of light is where that star was 4 years ago, not where it is now. The light from the nearest large galaxy to our own, a faint smear in the northern hemisphere, visible on dark nights, began its journey 2.5 million years ago, when our ancestors were first making and using stone tools. The universe you see when you look at that galaxy is the universe as it existed 2.5 million years in the past. The most distant objects visible to our best telescopes sent their light to us more than 13 billion years ago, when the universe was a fraction of its current age. A few 100 million years after the Big Bang, the photons that formed those images have been traveling ever since, stretching as space expanded, gradually dimming, finally arriving at our detectors after a journey that makes any other distance in human experience meaningless. When astronomers photograph the cosmic microwave background, the faint thermal glow released when the universe first became transparent to light, they are looking at the oldest light in existence. Those photons have been traveling for more than 13 billion years. They carry information about the universe as it was when it was only 380,000 years old. In those maps of the microwave background, the extraordinary smoothness of the early universe is visible. The low entropy beginning is literally visible in light that fills the entire sky. Looking outward through space is looking backward through time. And as you look further back toward that smooth, ordered beginning, you are following the thermodynamic arrow in reverse. tracing entropy back to its source. The further you look, the less entropy the universe contains, because the further you look, the closer you are to the starting point. This is why the universe is dark at night, a fact that troubled astronomers for centuries before anyone understood its significance. In an infinitely old, infinitely large, static universe, every line of sight would eventually end at the surface of a star, and the night sky would blaze uniformly bright in every direction. The darkness of the night sky tells us that the universe has a finite age and a finite history. The arrow of time has a beginning point beyond which we cannot see. The darkness is the shadow of the low entropy origin. Every time you lie in the dark and look up at the stars, you are observing the arrow of time written in light. The universe is showing you its history, layer by layer, all the way back to the extraordinary ordered beginning that made everything else possible. And somewhere in that ordered beginning is the answer to why you are here to look. Return one more time to the experiment beneath Geneva. The CPLEAR measurement was a genuine landmark. It placed in the hands of physics an empirical fact that had been expected but never directly observed. At the particle level, the laws of nature treat forward time differently from backward time. A microscopic arrow was measured, precisely, reproducibly, and beyond reasonable doubt. The result was confirmed at other laboratories, using different particles and different techniques. Experiments studying B mesons, particles containing heavier quarks, found much larger charge parity violations significant enough to attract serious attention as candidates for explaining the matter-antimatter asymmetry of the universe. The picture of time reversal violation in particle physics has grown considerably more detailed in the decades since CPLEAR announced its findings. But here is what the experiments cannot do. They cannot explain the large-scale thermodynamic arrow that governs your experience. The asymmetry measured by CPLEAR operates at the level of the weak force in specific processes involving specific particles that barely exist under normal conditions. It is a tiny, precise, technical asymmetry in the behavior of one type of decay process. The arrow of time that prevents broken glasses from reassembling, that moves you irreversibly from birth toward death, that carries the universe from its improbable beginning toward its inevitable end, operates on an entirely different scale and by an entirely different mechanism. The thermodynamic arrow is driven by the overwhelming statistical improbability of organized states compared to disordered ones. It requires no new forces, no particle asymmetries, no violations of any specific symmetry. It requires only that the universe began with very low entropy and that the second law of thermodynamics holds, which it does with absolute robustness at every scale we can observe. What the particle asymmetries do connect to is a different question. Why the universe contains anything at all after the Big Bang. The matter-antimatter asymmetry, which required charge parity violation of some form, is what left a residue of matter after the great annihilation of the first seconds. Without that asymmetry, even the thermodynamic arrow would have no matter to work with. And here, the CERN experiments reveal a significant gap. The charge parity violation observed in Kaons and B mesons is real, but it is too small by many orders of magnitude to account for the observed excess of matter in the universe. Something is missing. There are additional sources of asymmetry that the standard model does not predict and that no experiment has yet found. The Large Hadron Collider and the experiments running on it are searching for them. So, the picture is this. CERN found the microscopic arrow of time. The microscopic arrow connects to the matter-antimatter asymmetry. The matter-antimatter asymmetry explains why there is something rather than nothing, and the something that exists, having begun in a low entropy state, follows the thermodynamic arrow forward through time toward increasing disorder. Each step in this chain is established, but the connections between them, particularly the gap between observed charge parity violation and the actual matter excess, remain open. Physics is still following the arrow to its source. You are not merely a subject of the arrow of time, you are constructed from it. Every process that makes you what you are, from the chemical reactions producing energy in each of your cells to the electrochemical signals constituting your thoughts, depends on the thermodynamic gradient that the arrow of time represents. You exist because the universe has not yet reached equilibrium, and you exist in the specific form you take because entropy has been increasing in the particular way it has for 13.5 billion years. Consider what it takes to keep you alive through a single night. Your body maintains a temperature several degrees above the air around you, a gradient that requires continuous metabolic work to sustain. Your heart pumps rhythmically, maintaining pressure differentials that keep blood moving through a system of increasing complexity. Your brain consumes roughly 20% of all the energy your body burns, maintaining the low entropy neural patterns that constitute memory, thought, and perception. Where does all this energy ultimately come from? From the food you eat, which is organized chemistry, complex molecules assembled by the plants and animals you consumed, which obtained their organization from the nearest star through photosynthesis, or through eating things that used photosynthesis, all the way back to sunlight hitting a leaf. That starlight represents energy flowing from the hot surface of the nearest star into the cold darkness of space, a flow driven by the temperature gradient, a gradient that exists because the nearest star is burning hydrogen, which it is doing because the early universe produced hydrogen in large quantities, which it did because the Big Bang began in the specific low entropy configuration it had. Every breath you draw tonight connects, through this chain, to the first moment of the universe. The arrow of time is not an abstract feature of physics. It is the medium in which your existence is suspended. Every heartbeat, every thought, every second of this quiet night is part of the long process of converting the universe's initial order into disorder. This gives the concept of the present moment a strange weight. You are not merely in time. You are part of what time is doing. Your memories, your experiences, your capacity to lie here and wonder about physics, all of it is organized information maintained briefly against the overwhelming tendency toward disorder. The universe is, in this moment, organized into the form of someone thinking about whether organized forms are possible. There is something worth sitting with in this. The improbable beginning that started the arrow of time, that Roger Penrose calculated to be a probability with more zeros than there are particles in the observable universe. That beginning eventually organized itself into a star, and the star organized itself into a solar system, and the solar system organized itself into a biosphere, and the biosphere organized itself into a mind capable of calculating the probability of its own existence. The universe is not merely running down, it is, in the process of running down, briefly organizing into forms complex enough to understand why they are running down. That may be the strangest and most beautiful consequence of the arrow of time, and it has been pointing, without interruption, since the first moment of everything. Be clear about the edges of knowledge, because those edges matter as much as what lies inside them. The physics of the arrow of time is not a solved problem presented for your contemplation. It is an active frontier with genuine mysteries that the best physicists alive are still working to resolve. Mysteries where the competing ideas are serious, the evidence is incomplete, and the right answer is genuinely unknown. The deepest unresolved question is why the initial entropy of the universe was so low. Everything else about the arrow of time follows from this starting point. But the starting point itself is not derivable from any deeper principle that current physics can provide. It is an initial condition, a given, something the equations require but cannot explain. Cosmologists have proposed explanations, some involving quantum gravity, some involving eternal inflation, some involving the multiverse in various technical senses. But none of these proposals has been confirmed, and none commands consensus. The relationship between quantum mechanics and thermodynamics is another area of genuine uncertainty. The emergence of irreversibility from reversible quantum laws, while broadly understood through decoherence, involves subtleties that physicists continue to debate. How exactly does the quantum world give rise to the classical, irreversible world of everyday experience? The process of decoherence describes it qualitatively, but a fully rigorous derivation of classical thermodynamics from quantum mechanics, without any additional assumptions, remains an open technical problem. The role of gravity in thermodynamics is also incompletely understood. Gravity behaves oddly with respect to entropy compared to other forces. A uniform gas-filling space has high entropy in the ordinary thermodynamic sense, but low gravitational entropy, because gravity will eventually pull it into organized structures like stars and galaxies. The interaction between gravitational entropy and thermodynamic entropy, particularly in the context of black holes and the early universe, is an area of active research where the pieces have not fully assembled into a coherent picture. The black hole information paradox, the question of what happens to information that falls into a black hole, remains technically unresolved, despite decades of attention from some of the most brilliant theoretical physicists of the era. Its resolution will likely require a quantum theory of gravity that unifies general relativity and quantum mechanics, a theory that does not yet exist in complete form, and the matter-antimatter asymmetry, confirmed and quantified but not explained by the observed charge parity violations, points toward physics beyond the standard model, toward particles or interactions or symmetry-breaking mechanisms that have not yet been detected in any experiment. These are not small gaps in an otherwise complete picture. They are central questions about the nature of time, the structure of space, the origin of the universe, and the foundations of physical law. The arrow of time, for all its familiarity in daily experience, sits at the intersection of the deepest unsolved problems in physics. It is one of those places where the map of understanding runs out, and what lies beyond the edge is still being explored. The arrow of time is not only visible in the cosmic microwave background, or in the behavior of kaons in particle detectors, it is written into everything around you, if you know how to read it. Every object in the room where you are lying carries the thermodynamic history of the universe in its current state. The warmth of the bed against your body is heat flowing from a higher temperature region to a lower one, entropy increasing as thermal energy disperses. This process is irreversible in any practical sense. The heat that has left your body and entered the surrounding air has dispersed into the random motions of billions of molecules. It will not spontaneously reconverge and return to you. The wood or stone or metal of the walls around you carries the history of stellar nucleosynthesis. The atoms of carbon, oxygen, silicon, and iron that make up those materials were forged in the interiors of stars that lived and died long before the solar system formed. Each of those atoms carries, in its nuclear structure, a record of the temperatures and pressures of its formation. The fact that heavy elements exist at all is a consequence of the arrow of time. Stars could only form and burn and explode because the universe began with enough low entropy to permit gravity to create them. The electromagnetic signals carrying sounds and light through the air, the chemistry of every material in the room, the biological processes maintaining your body temperature, all of these are arrows pointing in the same direction, away from the past and toward the future, away from order and toward disorder, away from the improbable beginning and toward the probable end. Even the darkness between the stars carries information about the thermodynamic history of the universe. The cosmic microwave background fills all of space with a faint thermal glow at a temperature of just under 3 degrees above absolute zero. That temperature is not zero because the universe has not yet reached equilibrium. When it does, when the last energy gradients have dissipated and the last photons have been absorbed and re-emitted countless times, the temperature will be indistinguishable from absolute zero, and the background glow will fade into silence. The fact that it has not faded yet, that the background is still above absolute zero, that stars still burn, that chemistry still works, that you are still here to notice any of it, is a statement about where we are in the timeline of the universe's entropy increase. We are early. The arrow has been travelling for 13.5 billion years, but in terms of the full duration of the universe, from its low entropy birth to its high entropy death, we are at the very beginning. The story of entropy has barely started. This is, depending on how you look at it, either a sobering fact about the smallness of our position in the vastness of time, or an extraordinary privilege. The universe is at its most structured, its most varied, its most complex, right now, in this era of stars and planets, and chemistry and life. The arrow of time is carrying us forward, but where it is carrying us from is a place of remarkable richness, and the direction it is heading leads somewhere worth understanding. Step back from the technical details, from kaons and entropy and quantum correlations and the heat death of the universe, and ask the simplest version of the question that has been running through everything. Why does time move forward? The honest answer that physics can currently provide is because the universe began in a state of extraordinarily low entropy, and entropy has been increasing ever since. The arrow of time is the direction of that increase. The past is the lower entropy direction. The future is the higher entropy direction. Everything flows downhill from the improbable beginning toward the probable end. This answer is true. It is well supported by every observation and experiment ever performed. It connects the behavior of kaons in a particle detector to the cooling of coffee in a cup, to the formation of galaxies in the early universe. It is one of the most powerful unifying principles in all of science, but the answer contains a hidden recursion. The question of why entropy increases is answered by the low entropy beginning, and the question of why the beginning had low entropy is not answered. It is where the current map of physics runs out. Physicists can say what had to be true in order for the arrow of time to exist. They cannot yet say why those conditions were satisfied. Some find this incomplete answer sufficient. The universe began as it did. The arrow of time exists as it does. The fact that we exist to notice these things is inseparable from the fact that they are true. Asking why the initial conditions were what they were may be like asking what is north of the North Pole. There may simply be no prior context from which to answer. Others find the incompleteness unacceptable. Physics has a history of replacing unexplained initial conditions with derived consequences of deeper theories. The orbits of the planets, once an unexplained feature of the solar system, were derived from Newtonian gravity. The specific charges and masses of elementary particles, once unexplained constants, may eventually be derived from a deeper theory. Perhaps the low entropy beginning will one day be derived from a quantum theory of gravity, or from a cosmological framework that describes the birth of universes from a larger substrate. The experiment at CERN established that time is not symmetric at the particle level. The behavior of kaons carries a faint directional signal, a whisper from the asymmetric laws at the bottom of nature. That signal, amplified through the mechanisms of the Big Bang, helped create the universe of matter in which we find ourselves. That universe, beginning in its extraordinary low entropy state, has been running the arrow of time forward ever since. The arrow was there before the first atom cooled from the plasma of the Big Bang. It was there before the first star ignited. It was there before the first living cell assembled from the chemistry of a young planet. It will be there after the last star cools and the last black hole evaporates, and the universe reaches the equilibrium it has been approaching for longer than anything in nature has been able to measure. Time moves forward because it has always moved forward, and it will continue to do so because the conditions that established its direction are still in force. The question that launched this journey, the simplest question in physics, remains open at its foundation. And that openness is not a failure of physics. It is a sign that the most important questions are still being pursued. There is something quietly astonishing about the fact that the universe contains minds capable of asking why time moves forward. The process of asking the question requires memory, which requires entropy. The act of understanding requires a brain, which requires a body, which requires a planet, which requires a star, which requires a universe that began with extraordinarily low entropy 13.5 billion years ago. The question carries its answer inside itself, in the sense that only a universe with a thermodynamic arrow could produce the conditions for the question to be asked. Physicists at CERN will continue their work. The Large Hadron Collider will be upgraded in the coming years, its detectors made more sensitive, its beams more intense. New experiments will probe charge parity violations in new particles, looking for the additional asymmetry that explains why the universe chose matter over antimatter in quantities large enough to produce a world. New theoretical frameworks will be developed. New connections between quantum mechanics and thermodynamics and gravity will be explored. New observations of the cosmic microwave background will place tighter constraints on what the initial conditions of the universe actually were. The arrow of time is not just a philosophical curiosity or an abstract feature of physics. Equations. It is the condition for everything, for stars to burn and planets to form, and chemistry to organize into biology, and biology to organize into consciousness. For the tunnels under Geneva to be built, and for experiments to run, and for results to be recorded and transmitted and debated. For you to be here, in the particular configuration of matter and energy and information that makes you who you are. In this particular moment, on this particular night, the universe began improbably ordered. It is slowly, inexorably, sometimes magnificently running down. Between its improbable beginning and its inevitable end, there is everything that has ever happened or ever will happen. Every word ever spoken, every discovery ever made, every night ever spent lying in the dark, wondering about the nature of things. All of it exists because the arrow of time exists. And the arrow of time exists because something gave the universe a beginning worth running down from. The Kaon results, tiny and precise and revolutionary, confirmed that nature distinguishes between the past and the future, even at the most fundamental level. That distinction, amplified through the mechanisms of creation, produced a universe with matter to work with. That matter, beginning in its low entropy state, produced stars, and stars produced planets, and planets produced chemistry, and chemistry produced something that could wonder about the direction of time. Tonight is moving forward. Tomorrow is coming in the only direction time has ever moved. The arrow that began with the first moment of the universe is still traveling, carrying the cosmos toward its eventual equilibrium and carrying you with it through this quiet hour. The arrow points on, and for now, in this moment, in this extraordinary window of organized complexity that the universe has briefly managed to achieve, it carries you with it. Sleep, if you can, and let the arrow do what it has always done.